Hello everyone, welcome to chemistry lecture. And now I will discuss some questions in the chapter Electrochemistry. Okay, we can go to the questions. The first one, which of the following statement is not correct about an inert electrode in a cell? The first option, okay, it does not participate in the cell reaction. That's the correct statement. That is, an inert electrode will not participate in the cell reaction. That's the correct statement. Then the second statement, it provides surface either for oxidation or for reduction reaction. That is also a correct statement. It provides surface either for oxidation or for reduction reaction. Then we can go to the third statement, that is third option. It provides surface for conduction of electrons. Okay, that is also a correct statement. And the fourth one, it provides surface for redox reaction. That's a wrong statement. Okay, it provides surface either for oxidation or for reduction reaction. That's why the fourth statement is incorrect. But our question is, which of the following statement is not correct? That is incorrect statement. Therefore, our option D is the correct answer. That is the incorrect statement. Clear? Then we can go to the next question. The second question, an electrochemical cell can behave like an electrolytic cell when the first option, the cell potential is equal to 0. Second option, cell potential is greater than external potential. Then the external potential is greater than cell potential. Then cell potential is equal to external potential. Okay? As the first condition, that is the cell potential is equal to 0. The condition is equilibrium. That is the equilibrium condition. Okay? And second option, the cell potential is greater than external potential. At this condition, the cell will act as an electrochemical cell. Okay? That is, it will act as a galvanic cell. Okay? That means the electron will flow from anode to cathode, and there will be a current flow from cathode to anode. Okay? In the case of a Daniell cell, the zinc ions will go to the solution and copper ions or copper metal deposit on cathode. That is, it will act as a galvanic cell. Then option C, that is when external potential is greater than cell potential. At this condition, the cell will act as an electrolytic cell. Electrolytic cell. Okay? And fourth option, if the cell potential is equal to external potential, at this condition, there is no current flow and the cell will be in off state. No current flow. Okay? And the question, an electrochemical cell can behave like an electrolytic cell when, that is the third option, that is external potential is greater than cell potential. Therefore, our correct answer is option C. External potential is greater than cell potential. At this condition, the cell will behave as an electrolytic cell. Clear? Then we can go to the next question. The question is, using the data given below, find out the strongest reducing agent. Find out the strongest reducing agent. Okay? The reduction potential is given. The first option, it is 1.33. Second option, 1.36. Third option, 1.51. And the fourth option, it is minus 0.74 volt. Which one is the strongest reducing agent? Okay? I will give you a hint. That is, the lowest reduction potential element. Okay? or least reduction potential element or metal will undergo oxidation, and it will act as a strong reducing agent. Okay, strong reducing agent. If it is a strong reducing agent, then we can also say that it is a weak oxidizing agent. Weak oxidizing agent. Then in the case of a highest reduction potential metal, the highest reduction potential metal will undergo reduction, and it will act as strong oxidizing agent. Okay, strong oxidizing agent. If it is a strong oxidizing agent, we can say that it is a weak reducing agent. Weak reducing agent. Okay, this is the hint for this question, that is, the metal having least reduction potential or lowest reduction potential will act as strong reducing agent, and highest reduction potential metal will act as strong oxidizing agent. Then we can go to the question. Using the data given below, find out the strongest reducing agent. Look at the options. Here minus 0.74 is the least reduction potential. Okay. Therefore, we can say that the least reduction potential is for chromium. That is, option B is the correct answer. Clear? Then the next question. The quantity of charge required to obtain 1 mole of aluminum from Al2O3 is. The quantity of charge required to obtain 1 mole of aluminum from Al2O3. Okay. First of all, we can write the reduction reaction of aluminum ion. Okay. That is the preparation of 1 mole aluminum metal. In Al2O3, we will get Al3 plus ion. Therefore, we can write Al3 plus ion accepts 3 moles of electron and will become aluminum metal. Okay. Then here you can see that 1 mole aluminum is produced. Okay. 1 mole aluminum is produced by how many moles of electrons? Here you can see that 3 mole of electrons. 1 mole of aluminum is produced by 3 mole of electron. Therefore, the question is find out the charge required to produce 1 mole of aluminum. Okay? That is the charge of 3 mole electrons. The charge of 1 mole electron is 1 Faraday. Therefore, the charge of 3 mole electron is 3 Faraday. It's a simple question. Okay? Charge of 1 mole electron is 1 Faraday. Therefore, charge of 3 mole of electron is equal to 3 Faraday. Therefore, our correct answer, it is option C, 3 Faraday. Clear? Then the next question. Lambda 0m NH4OH is equal to. Okay, we need to find out the limiting molar conductivity of NH4OH, ammonium hydroxide. Okay, according to Kohlrausch's law, the limiting molar conductivity of an electrolyte is equal to the limiting molar conductivity of individual ions in the solution. Okay, for example, limiting molar conductivity of aqueous NaCl. Okay, that is lambda 0m NaCl. According to Kohlrausch's law, the limiting molar conductivity of an electrolyte is equal to the sum of limiting molar conductivities of individual ions. this NaCl molecule will give one Na plus ion and one Cl minus ion. That is one cation and one anion. Therefore, we can write lambda 0 m Na plus cation, that is limiting molar conductivity of sodium cation, plus limiting molar conductivity of chlorine anion. Okay. Here we can check the first option, that is lambda 0 m NH4OH plus lambda 0 m NH4Cl minus lambda 0 m HCl. Okay. Before that, we can write the limiting molar conductivity of NH4OH. Okay. That is according to Quadrature's law, we can write lambda 0 m NH4OH is equal to lambda 0 m of NH4 plus, that is the cation, plus lambda 0 m of OH minus, that is the limiting molar conductivity of anion. Then we can check the first option. Okay. The first option is lambda 0 m of NH4OH plus lambda 0 m of NH4Cl minus lambda 0 m of HCl. Okay. We can write lambda 0 m of NH4OH plus lambda 0 m of NH4Cl minus lambda 0 m of HCl. Okay. We can split this equation, that is lambda 0 m of NH4OH is equal to lambda 0 m of NH4 plus lambda 0 m of OH minus plus lambda 0 m of NH4 plus lambda 0 m of Cl minus. Okay. Then minus of lambda 0 m of H plus minus lambda 0 m of Cl minus. Okay. Here limiting molar conductivities of chlorine will cancel. Then this form is not equal to limiting molar conductivity of NH4OH. Okay. Therefore, we can cancel option A. Clear? Then we can go to the second option. Okay. What is the second option? Lambda 0 m of NH4Cl plus lambda 0 m of NaOH. Okay. Lambda 0 m of NH4Cl plus lambda 0 m of NaOH, then minus lambda 0 m of NaCl. Okay. Minus lambda 0 m of NaCl. Okay. We can split this equation according to Quadrature's law. We can write lambda 0 m of NH4 plus lambda 0 m, that is option B, m of Cl minus plus lambda 0 m of Na plus lambda 0 m of OH minus of lambda 0 m of Na plus minus lambda 0 m of Cl minus. Okay. Here limiting molar conductivities of sodium will cancel, then Cl minus we can cancel, limiting molar conductivities of chlorine, then we will get lambda 0 m of NH4 plus lambda 0 m of OH minus. Okay. We can write lambda 0 m of NH4 plus lambda 0 m of OH minus equal to lambda 0 m of NH4OH. That is, we can write lambda 0 m of NH4OH. That is, option B is equivalent to limiting molar conductivity of NH4OH electrolyte. That is, our correct option is option B, lambda 0 m of NH4Cl plus lambda 0 m of NaOH minus lambda 0 m of NaCl. Clear? Then the next question. Okay. In the electrolysis of aqueous sodium chloride solution, which of the half-cell reaction will occur at anode? Okay. I will explain the electrolysis of aqueous NaCl solution. The NaCl molecule will give Na plus ion and Cl minus ion. That is, NaCl will dissociate into Na plus ion and Cl minus ion. Okay. It is an aqueous solution, and this solution contains water molecule. Water molecule dissociate into H plus ion and OH minus ion. That is, aqueous NaCl will produce Na plus, Cl minus, H plus and OH minus ion. Okay. In an electrolysis reaction, we use an electrolytic cell. In an electrolytic cell, it contains two electrodes, anode and cathode, and the anode electrode is positive. Okay. Anode electrode is positive in an electrolytic cell, and the cathode electrode is negative. But in the case of galvanic cell, the anode is negative and cathode is positive. In the case of an electrolytic cell, anode is positive, cathode is negative. Okay. And the reaction at anode is oxidation. That is, anode electrode undergoes oxidation, and the reaction at cathode is reduction. Okay. Then anode terminal is positive and cathode terminal is negative. Therefore, the oppositely charged ions move towards the anode terminal. That is, the negatively charged ions, that is Cl minus and OH minus ions, move towards anode terminal. Okay. And the positively charged ions, that is H plus and Na plus ions, move towards cathode. Okay. At anode, one anion will undergo oxidation and other will go to the solution. At cathode, one cation will undergo reduction and other will go to the solution. Okay. That based on the reduction potential and oxidation potential of ions. At anode, oxidation reaction takes place. The highest oxidation potential is for chlorine as compared to OH minus. OH minus has least reduction potential, oxidation potential. Okay. Therefore, the chlorine ion will undergo oxidation, that is Cl minus will lose one electron and will become a chlorine atom. Okay. And the OH minus ion will go to the solution. And here the reduction potential of hydrogen is greater than sodium. Okay. The hydrogen has highest reduction potential and sodium has least reduction potential as compared to hydrogen. Therefore, hydrogen will undergo reduction. The H plus ion will accept one electron and will become a hydrogen atom. Okay. And the sodium cation will go to the solution. Okay. That means after the electrolysis of aqueous NaCl solution, chlorine gas will be liberated at the anode and hydrogen at cathode, and the solution will become sodium hydroxide. Okay. NaOH, aqueous solution. Therefore, we can go to the question. In the electrolysis of aqueous sodium chloride, which of the half cell reaction will occur at anode? At anode, chlorine undergoes oxidation. That is, our correct answer is option D. Cl minus gives half Cl2 plus 1 electron. That is oxidation reaction of chlorine. Okay. Then the next question. Okay. The standard reduction electrode potentials of Fe2 plus bar Fe and Sn2 plus bar Sn are minus 0.44 volt and minus 0.14 volt. What will be the EMF of the following cell reaction? Okay. The cell reaction is given Fe2 plus Sn gives Fe plus Sn2 plus. We need to find the EMF of the cell reaction. Okay. First of all, we can write the overall reaction. The overall reaction is Fe2 plus Sn gives Fe plus Sn2 plus. Okay, this is the overall reaction. Then we can write the reduction reaction of iron and tin. Okay, it is Fe2 plus 2 electron. Fe2 plus accepts 2 electron and will become iron metal. Okay, here it is in solid state, here it is in aqueous state. Aqueous, solid, solid, aqueous. Okay, and this equation we can denote it as 1. Then Sn2 plus accepts 2 electron and will become Sn solid. This is equation 2. Okay, and the overall reaction, it is equation 3. Okay, look at the 3 reactions and find out the relationship between these 3 reactions. You can see here, if you subtract reaction 1, if you subtract reaction 2 from 1, you will get reaction 3. Okay, if you subtract equation 2 from equation 1, we will get equation 3. Okay, we can check equation 1. The reactants are Fe2 plus 2 electron minus the reactants in the second reaction Sn2 plus minus 2 electron gives Fe minus Sn. You can cancel the number of electrons. Fe2 plus and Sn will go to the reactant side and Sn2 plus will go to the product side. Sn2 plus Fe. That is the overall reaction. Okay, that is the relationship between these 3 equations are 1 minus 2 is equal to 3. Okay, therefore we can write the standard Gibbs free energy change. Okay, that is delta G03. That is the standard Gibbs free energy change of third equation is equal to standard Gibbs free energy change of first equation minus standard Gibbs free energy change of second equation. And what is delta G0? The relationship between standard Gibbs free energy change and cell potential, that is equal to minus NF E0 cell. We can substitute here minus N3 F E0 3 is equal to minus N1 F E0 1 minus minus plus N2 F E0 2. Okay. Here look at the number of electrons. that is N3, N1 and N2. The number of electrons is equal to 2, therefore we can cancel number of electrons and Faraday's constant, and the equation will become minus E03 is equals minus E01 plus E02. Okay? And we can substitute the values, or we can write E03 is equals E01 minus E02. Okay? And what is E01? That is reduction potential of ion, that is minus 0.44, minus of reduction potential of tin, that is 0.14, and we will get minus 0.44 minus minus plus 0.14, and we will get the final answer, that is minus 0.30 volt. Okay? Then we can go to the options. Minus 0.30, that is option D is the correct answer. Clear? The correct answer is option D, that is minus 0.30 volt. Clear? Then we can go to the next question. A standard reduction electrode potentials of 4 elements are, the first one, element A, reduction potential minus 0.250, B minus 0.140, C minus 0.126, D minus 0.402 volt. And the question is, the element that displaces A from its compounds, aqueous solution is. Okay? I will give a hint for this question, that is the least reduction potential metal, okay, or the lowest reduction potential metal will displace highest reduction potential metal, okay, highest reduction potential metal from its solution, okay. The lowest reduction potential metal will displace highest reduction potential metal from its solution, okay. Then we can go to the question. The element that displaces A from its compounds aqueous solution is. Here look at the electrode potential or reduction potential of element A. Here it is minus 0.250 volt. Okay. Then look at the reduction potentials of other elements. Option B, it is minus 0.140. It is greater than A. Therefore, we can neglect option B. Then option C, minus 0.126 volt. This value is also greater than reduction potential of A. Therefore, we can neglect option C. Element C. Then D, it is minus 0.402 volt, which is lesser than element A. Okay. Therefore, our correct answer is element D, which has a reduction potential lower than A. Therefore, our correct answer is option C, that is the element D. Okay. The least reduction potential element D will displace the highest reduction potential element A from its solution. Clear? Then the next question. Okay. The standard potential E0 for the half reactions are as. The first half reaction, Zn gives Zn2 plus 2 electron. Zn gives Zn2 plus 2 electron, that is losing of electron. Losing of electron is oxidation. For this reaction is oxidation. Therefore, this potential will be oxidation potential. This potential is oxidation potential. Okay. And Fe gives Fe2 plus 2 electron. This reaction is also oxidation. Okay. This reaction is also oxidation. Oxidation. Therefore, this potential will be oxidation potential. Okay. Therefore, we can write the reduction potential of zinc and iron, that is oxidation potential is equal to minus of reduction potential. Therefore, the reduction potential of zinc will be minus 0.76 volt and the reduction potential of iron, it is minus 0.41 volt. And what is the cell equation? That is highest reduction potential minus lowest reduction potential, or E cathode minus E anode, or we can write E right minus E left. Highest reduction potential minus lowest reduction potential. Okay. Therefore, highest reduction potential, it is for iron minus 0.41, minus 0.41 minus 0.76. We will get minus 0.41 plus 0.76 and the value will be plus 0.35 volt. That is plus 0.35 volt is the EMF of this cell. That is our correct answer is option B, that is plus 0.35 volt. Clear? Then the next question. Okay. The standard oxidation potential of zinc and silver in water at 20 degrees Celsius are Zn gives Zn2 plus 2 electron, Ag gives Ag plus 1 electron. Okay. Zinc reduction potential, the potential is 0.76, not the reduction potential, because the reaction is oxidation. Clear? That is losing of electron occurs. Here look at the oxidation potential. From this data we can write the reduction potential of zinc and silver. The reduction potential, here the potential is oxidation potential. Reason, this reaction is oxidation, that is losing of electron occurs. The reduction potential will be minus of oxidation potential. Oxidation potential is 0.76, therefore reduction potential minus 0.76. And the oxidation potential of silver is given minus 0.80, therefore reduction potential will be plus 0.80 volt. Okay. Then the least reduction potential will undergo oxidation and highest reduction potential element or metal will undergo reduction. Clear? The least or lowest reduction potential metal will undergo oxidation. Okay. Look at here, the least reduction potential is for zinc, therefore zinc will undergo oxidation, therefore we can write the oxidation reaction of zinc. That is Zn gives zinc will lose 2 electron and will become zinc metal. Zinc 2 plus ion. It is in aqueous state and zinc it is in solid state. Then highest reduction potential metal will undergo reduction. Okay, reduction. The silver reduction potential is plus 0.80. Therefore, silver will undergo reduction. Therefore, we can write the reduction reaction of silver. Ag plus accepts one electron and will become silver metal. And you can see here the number of electrons loosed by zinc, it is 2 electrons, here it is 1. Therefore, to equalize the losing and accepting the electrons, we need to multiply it with 2. You will get 2 Ag plus 2 electron gives 2 Ag. Okay. Then we can combine these two equations and we will get the overall reaction. In the first reaction, the reactant is zinc. In the second reaction, the reactant is 2 Ag plus. Okay. And we can cancel the number of electrons. Gives 2 Ag plus Zn2 plus. That is the overall reaction. This is the overall reaction. Then go to the options. Zn plus 2Ag plus gives Zn2 plus 2Ag. That is, the first option is the correct answer. Option number A. Okay. Then the next question. Okay. The next question. Which one liberates bromine from KBr? The options Hi, I2 iodine, chlorine and sulfur dioxide. Which one will liberate bromine from KBr? Here it depends on the oxidizing power. Okay, we need to find out which one is or which one has highest oxidation power than bromine. Okay, here the chlorine is more powerful oxidizing agent than bromine. Okay, the chlorine is more powerful oxidizing agent than bromine. Therefore, chlorine is highly reactive than bromine. This chlorine will displace bromine from KBr. That is, due to the high reactivity of chlorine, when KBr reacts with chlorine molecule, the chlorine will displace bromine and will become KCl and remaining bromine. Okay, and you will get the remaining byproduct as bromine. Reason, chlorine is highly reactive than bromine. Okay, and oxidizing power of chlorine is greater than bromine. Therefore, the chlorine will displace bromine from KBr. Okay, I hope it is clear. Therefore, our correct answer is option C, chlorine. Chlorine will liberate bromine from KBr. Okay, I hope it is clear, and I will discuss some more questions in the next lecture. And all of you, thank you for watching. Thank you all.